So here we are done, but we can make the expression a little bit simpler just by exploiting the properties. Here it is a very last step, you see, going from here to here. We just exploit the properties that the cosinus square of theta plus sinus cosine to the power of 2 of theta is equal to 1. So we just use this expression to go from this step to this other step. Let's clean up. Last step. Here we have the coefficient, the only non-zero coefficient of our curvature form. We now can compute the Ricci tensor components. So here we go. We have only 2, 1, and therefore the only Ricci components that we can possibly have are the 1, 1 and the 2, 2. They are computed just by, that's a 2 form. Therefore, it's going to swallow 2 vectors, and these are going to be the basis vector of our Cartesian frame. So we just use the explicit expression of omega that we derived earlier, so down here, so that's just that. And we now just apply the product of theta 1. So you see we have, remember that here we have, we're just using the explicit expression for the exterior product, the theta. Remember that we basically have theta 1, theta 2 minus theta 1, theta 2. That's the definition of theta 1, theta 2. Okay? So we are just doing that, going from here to here. Plus, we keep in mind that theta Ej is equal to delta Ej. So we are just using these two definitions. They are constructed like that. That's the definition of the exterior product, and that's what we use to go from here to here. Then we just look at the deltas, and we have delta 1, 1 is equal to 1, delta 2, 2 is equal to 2, and then these are equal to 0. 2, 1, 1, 2, two indices that are different than 0 are equal to, that are different one from each other. This gives us a 0. We are left only with 1. And the same goes for the 2, 2 components. Okay? No surprise, we get 1 and 1 for our Ricci tensor components. Then we need the Ricci scala. We just go for the usual contraction. Here it is. We get a 2, and then we just use the definition of the Einstein tensor, which is down here. We just plug in our for the 1, 1 component. We just plug in R1, 1, which is equal to 1, and then we have minus 1/2 times 2, right? The 2 is coming from the Ricci tensor, which gives us a minus 1, and give us, in the end, a component which is equal to 0. The other non-zero component of the Einstein tensor would be the 2, 2, but also this one is equal to 0. Because we again 1, 1, and 2, guess what? We get exactly the same values of the 1, 1 component. That's it. So I just summarized the steps. It's very simple. You're using the Cartan formalism. It's not complicated because everything is based on the first and second structure, Cartan structures equation. Okay? On these two expressions. That's it. Once we have that, remember that in GR or on these Euclidean manifolds, we have curvature, the torsion is equal to 0, and this easily allows us to compute the spin connection omega. First step, define the basis, the optimal basis such that this expression holds, okay? Meaning whatever you have for your two interval, you must get something like that. So look at the expression in your standard expression of the two interval to get this equation with this form, with this structure, and here you get your basis. Then you just need to compute the derivative of your basis to fill it up in your Cartan structure equation. Then you isolate this omega term to have the component, the coefficients of your spin connection. Done up to this point. Now you use the second Cartan structure equation, this one and this one, so the spin connection, we already computed it. Just go for the derivative, for the exterior derivative of your spin connection, for your form connection, and that's what you get. Once you have your curvature, your form curvature, you just project it on the Cartesian basis. You can perform then the contraction of, once you have your Ricci tensor, you perform the contraction to get the Ricci scalar, use the definition of the Einstein tensor, and you are done.